This is lesson 4.1, rational functions. So starting a new chapter here, start a new section in your notebooks, and we will get this one started. All right, so on page 312 in your book, rational numbers we've talked about in our past before, so that's a wording that you should be familiar with. Remember that rational numbers were anything that can be written in the form of a over b. Okay, so rational numbers were anything that could be written like a fraction. So it would make sense then that in this section where we're going to talk about rational functions, we're going to have functions that are written with both a numerator part and a denominator part. So our book uses the notation for a numerator function. They're going to have n of x and denominator function d of x. So those two things are no fancier than strictly telling you you have a numerator part and a denominator. Now we're going to need to watch that denominator so it does not equal 0. Okay, you guys know whenever we're talking about rational expressions or things that have denominators, we have to avoid those undefined. So you could well imagine that we are going to be thinking about domains again. Now, when we graph these rational functions, we're going to be discussing the behavior of the functions. Well, we've already been talking back in chapter 3 about that left and right hand behavior of those other kinds, those polynomial functions. So we're already used to looking at that sort of thing when we're discussing a graph. So to figure out how the graph of the function is going to look, find the domain. Then choose lots of values that lead into any excluded values coming at that number from the left and from the right. Figure out what the curve or the graph is going to do as you get closer to that undefined number. So let's take a look on page 312. There's one problem that's done for you in your book. You can see the tables there where they've chosen many values. We're going to do the same kind of consideration here. So if we are trying to, let me move this out of the way a little bit, find the domain, again we're focusing on the denominator of this fraction. You see an x minus 1 there. So the zeros of our denominator, we're going to have a value of x equals 1 that we have to avoid. So our domain is all real numbers but x cannot equal a 1. Okay, so as we get closer and closer and closer to an x value of 1, what's our graph going to do? All right, so I created a table of values, and you can check me on this, but I came at my 1 from the left. So I started back at -1 and 0, and then I did a lot of decimals that got me closer, well not a lot, a couple, that got me closer and closer and closer to that 1. Then on the other side, I picked 1.1, 1.3, a couple that were really close to the one on the right. And then I broke myself away. And I suppose I could have used a lot of smaller-ish ones too, but I went into a couple that were quite a bit bigger. All right, so at -1, I got 1.5. 0 was 0. -3, -7, I'm going to quickly fill in my table here. So getting a sketch going here then, at -1 I was at 1.5, 0, 0, and see how when I crept in a little bit, I went down quite quickly as I got closer to that value of 1. So you can see what this curve is going to do. It's going to come in here from the left and it's going to drop off drastically. On the other side, it starts in real high off my graph paper. 1.3 would put me up here somewhere. 1.5. Oops, my pens aren't lining up real great here, folks. 1.5 was right about at 9. 2 was at 6. 4 was at 4. 6 was at 3.6. And I think you can see here that this curve is going to level off as well. Now we're going to make a bit of a conjecture for right now, and I'm going to show you how we're going to determine this here in just a little bit. But it flattens out and never quite hits that 3 line. All right, so like I said again, we'll come back to that horizontal that it doesn't make to in just a second. But you can see here we have really drastic ends as we're getting closer and closer and closer to that 1. So what is a line like that called then? They are called asymptotes. I think that's going to be familiar to you from the past with Algebra 2. Your behavior of a function as x nears an asymptote has a notation that's used to describe it as well. So if you guys look with me on page 313 at the top, it's in red print up there, the wording that goes along with this notation. But if we think back to that graph that we just made, f of x, or my y values, this little arrow thing, you use the words heads to or goes to or approaches or whatever. I like goes to. So y goes to negative infinity as x nears 1 from this little negative sign means we came at our 1 from the left. Okay, so then the second line there said that our y values, or our f of x, goes to positive infinity as x went to 1 from the right. Okay, so as we closed into it coming from the right, it went sky high real fast. It went to positive infinity. Okay, so that's just a little bit of a notation for you. So asymptotes for that checkpoint number 1 can then be determined. Okay, so since 1 was an undefined value that our graph never crossed, never quite reached, the line x equals 1 is considered a vertical asymptote. Like we saw from our picture, our y value also doesn't quite ever touch 3. So the line y equals 3 is going to end up being a horizontal asymptote. And again, just hang tight for just a bit more and I'll show you how we can calculate that y equals 3 line also. So a little bit of a summary box. I'm getting my information for this box on the top of page 314. You can see it there. I think this maybe is a little bit clearer than looking at all the fancy notations and function notation that's in there. So if you're looking simply for a vertical asymptote, those are going to be the zeros of your denominator. Okay, so the excluded values from your domain form or find our vertical asymptotes for us. Okay, vertical asymptotes, look for the zeros in your denominator. Look for your undefined values in the denominator. Horizontal ones, okay, so now we're finally back to that. To determine horizontal asymptotes, you're going to look at the degree of both the numerator and the denominator part of your function. Okay, if the numerator has a smaller degree than the denominator, y equals 0 is going to be your horizontal asymptote. Okay, remember the y equals 0 line, that's your x-axis. So if the numerator has a smaller degree than the denominator, the x-axis will be a horizontal asymptote. Your graph is not going to cross it. B, if the degrees are the same, okay, so if they match, then your horizontal asymptote is going to be the ratio of the lead coefficients. Okay, so if the top function has a squared value and the bottom function has a squared value for the highest powers, okay, you take the coefficients of those two parts, make a ratio, that y equals a over b is your line. C, if the degree of the numerator is bigger than the denominators, there isn't one. Okay, so oftentimes there won't be a horizontal asymptote, and that's the reason why. If your numerator degree is bigger than the denominator, you're not going to find one. So let's practice this. Find all vertical and horizontal asymptotes of the graph of f of x equals 5x squared over x squared minus 1. So looking for vertical first. So remember, vertical asymptotes are tied to the denominator and figuring out our domain. So right now I'm seeing x squared minus 1 in my domain. I need my zeros for that. So I'm going to factor. It's a difference of perfect squares. It factors into this. I can see 1, 0 at negative 1. another 0 at positive 1. So I have two vertical asymptotes. I have the x equals negative 1 line. I also have the x equals 1 line. Okay, my graph is never going to quite reach those vertical lines. Horizontal asymptote. Okay, so looking at my functions, I have 5 to the x squared power, and the bottom one is an x squared power as well. So notice that my degrees match. So if you look back or think back to the notes that you just took, when the degrees match, your horizontal asymptote is equal to the ratio of your lead coefficient of the numerator to the lead coefficient of the denominator. So the lead coefficient on top is 5, the lead coefficient on the bottom is a 1. So y equals 5 is my horizontal asymptote. Okay, now scroll back real quick. Let's look at that checkpoint problem one more time. One more, here we go. When we were looking at our degrees, we had degree of 1 on top, degree of 1 on the bottom. So our horizontal asymptote, since the degrees matched, would be 3 over 1, or y equals 3. Okay, I said we'd get back to that. So that's mathematically how you find that horizontal asymptote. Okay? Let's do it for this one here. Okay, so vertical ones first. At least I always find them first. I need to find those excluded values for my domain. So my denominator function is x squared plus 4x plus 3. It's looking factorable, so it's looking like we're going to have some zeros. So we have a negative 1 and a negative 3. So we have two vertical asymptotes. X equals negative 3 and x equals negative 1. Okay, horizontal. Again, we have a match with our degrees. So we're going to find our horizontal asymptote with that ratio again, a over b. Okay, we have a lead coefficient of 3 here and a lead coefficient of 1 here. So y equals 3 will be your horizontal asymptote. All right, so a couple of applications. Checkpoint number 4 goes along with another cost-benefit model that's above it in the textbook. But taking a look at this cost function, it says the cost C in millions of dollars of removing P% of the industrial and municipal pollutants discharged into a river is given by C is equal to 255P over 100 minus P. Okay. Now, the percentages here are limited to looking at positive values. You can't remove a negative percent of pollutants. And we're going to talk about the 100% fact in that they tell us we can't plug 100 in here in part B of this question. All right, so let's find the cost of removing 20%, 45%, and 80% of the pollutants. Now, before we even begin this, let's make a guess. Okay, cost to remove more pollutants from the air. So would your best guess be that the cost will rise or fall with the amount of pollutants that you're trying to get out of the air or get out of the river? You know, in my head, I'm assuming that if we take out more pollutants, it's going to cost us more money to do so. So let's see if our calculations end up showing us that same thing. All right, so plugging 20% in first. Okay, doing the math here, I come up with $63.75. Okay, at 45%, let's redo it. I end up with $208.64, roughly. And then it said to do 80%. And this one came in at $1,020. Okay, so like in my head I guessed, or I assumed, the cost definitely does go up quite dramatically with increased percentages of pollutants that we're trying to remove so that they don't discharge into this river. Now, let's go to the 100% thing. Now, if you strictly look at this mathematically, um, our model tells us that we can't use a 100 because if you look at or look for asymptotes, we cannot put a 100 into this function, period, because it would create a 0 in our denominator. So according to the model, would it be possible to remove 100% of the pollutants? No. Um, you know, if you look at it scientifically, I don't think it's possible to get everything out. Plus, if we're just based on the model, 100 is going to be an asymptote. Okay, it's a vertical asymptote. We can't cross that line, so we can't input 100. Checkpoint number 5. Okay, so flip the page. We've got this last one to do. In this one, it says a business has a cost function of C is equal to 0.4x plus 8,000, where C is measured in dollars and x is the number of units produced. The average cost per unit is given by 0.4x plus 8,000 over x, when x is greater than 0. Again, that x is greater than 0, you don't have to worry about it a whole lot. It's just you can't make a negative amount of units. You have to make something. All right, so you know you're going to produce a positive number of units. That's why the x greater than 0 is there. All right, so using our model, we're going to find the average cost per unit when we have 1,000 units, 8,000 units, 20,000 units, and 100,000 units. Okay, so doing our math, okay, this one calculates to 8.4. If I do this for, whoops, if I do this for 8,000 next, okay, so at 8,000 units, I get 1.4. 20,000, plug that one in next. I calculated 0.8. And the last one they gave us was 100,000 units. And I got 0.48. Okay, so it's looking like the cost is going to decrease as the amount of units that we produce goes up. Okay, now letter B said, what is the horizontal asymptote for the function? So again, when we're determining that horizontal, we want to look at the degrees of our numerator and denominator functions. The numerator has a degree of 1, so does the denominator, so they're a match. Remember that when your degrees match, your horizontal asymptote is going to be a ratio of your numerator to your denominator. So my asymptote ends up being y is equal to 0.4. We'll never quite reach that y value. Okay. Page 317 is the beginning of your practice, so make sure you guys give this a try. Section 1 is kind of the nice short section. Try to really get a handle on this asymptote idea, where your horizontal and vertical asymptotes come from, because those will be coming into play as we go into our conic functions and stuff for the rest of the chapter. So come on in and ask questions if you have any. I will see you guys in class.